Hi, I'm Pei Wang from Google. Today I'm going to talk about our experience with preventing DOM-based cross-site scripting in large-scale web development with a technique called API hardening. For those who are not already familiar with the matter, cross-site scripting, usually abbreviated as XSS, is a type of injection attacks in which malicious scripts are injected into benign and trusted websites and get executed as part of that website. XSS has been one of the most common web security vulnerabilities for a long time. Let's see some data about its popularity. Google has a vulnerability reward program to recognize outside researchers who report security problems found in Google's products. In 2018, over 35% of the dollar amount of the reward goes to XSS bugs. Well, you can say maybe it's just Google engineers are bad at writing secure web applications, but unfortunately, other data suggests this is a universal problem. Here's a breakdown of the top reported vulnerabilities on HackerOne, one of the most popular bug bounty platforms. Being the number one category, XSS contributes to 23% of the reported vulnerabilities. So it's not just a Google problem. There are three types of cross-site scripting. The first two are called stored and reflected XSS. We're not going to talk a lot about these two types today. Just remember that they require interactions with servers from the clients. A more interesting type is the DOM-based XSS. It has several characteristics worth mentioning. First, exploiting those doesn't necessarily require interactions between servers and the clients. Second, the sinks into which the malicious data flow are inside the browser. And third, as in single-page web applications become more and more popular, DOM XSS tends to be the dominant type of the XSS variant. So how does DOM XSS happen exactly? In some sense, you can say DOM XSS happens because DOM APIs do not distinguish malicious and trusted input. With native DOM APIs, user-controlled strings can easily get interpreted as HTML or JavaScript code. The injected code executes in the same origin of the website, therefore bypassing the same origin security enforcement. Take an example here. The JS code of a web application takes part of the URL, which is user-controlled, and assigns it to the inner HTML property of an element in its page. Attackers can plant arbitrary executable content in the URL, like event handlers in this case, and once that vulnerable code is executed, the user-injected content will get executed as well. As you can imagine, a vulnerability as prevalent as XSS must have been tackled in many ways. People have tried static analysis, testing, in-browser defenses like content security policy. Many of these mitigations work, but none of those work well enough to help get rid of XSS from modern web applications for different reasons. At Google, we're taking a new approach to exterminating XSS. We call the method API hardening. The idea of API hardening is inspired by lessons we learned from years of experience with fighting XSS in industry. First, we know that web applications are becoming huge and complex. Tests and human reviews combined are not sufficient to prevent the vulnerabilities from slipping into your codebase. Second, countless examples have shown that it's almost always easier and cheaper to fix security problems early, before the software gets shipped into production. And we notice that compiler errors are usually more actionable for developers comparing with other signals. So that's how we develop this idea of making DOM APIs inherently secure, so that developers can't write XSS-prone code in the first place. The basics are simple. We first extend the compilers to forbid uses of native DOM APIs that can easily cause XSS. We then design alternative APIs that are impossible to write excess vulnerable code with. Technically, there are three major components of the hardened APIs. First, we have safe types, which annotate the values that are proven to be safe to be fed into the DOM or JavaScript engine. Second, we have safe builders. These are factory functions that produce safe type values. In fact, they are the only source of safe type values. You can't build safe type values in any other way. And finally, there are safe sinks. These are the secure alternatives of the original DOM APIs. They only accept safe types values instead of strings. Let's see an example of the hardened APIs. At the top, there are two access-prone DOM APIs, window location href and document write. Both APIs take strings and interpret them as URLs or HTML. At the bottom, there are the hardened APIs. You can see that the new APIs take safe type values as parameters instead of plain strings. So before using these APIs, developers have to use our safe builders to construct safe type values from potentially malicious strings, either by sanitizing them or making it clear to compilers that the strings are constant and not user controlled. At Google, the code on top cannot be compiled because we bind those dangerous APIs in the compiler, and that's how we make sure everyone is using the secure APIs. The hardened APIs look good so far, but the real challenge is how to migrate developers off the original APIs and make sure they know how to use the new APIs without impacting their productivity, especially for an organization as large as Google. We offer various of supports in accordance with the hardened APIs like documentation, Q&A services, automatic code fixing tools. Since the hardened APIs are meant to be secure, they can be very restrictive as well. And sometimes they are not expressive enough for certain developers, and they have to use the original APIs. We have a small group of security experts to handle all these kind of reviews and exception requests. Another point worth mentioning is how we deal with legacy code. By the time of we deploying API hardening, there is already a huge amount of legacy code that can't be immediately revised to use the new APIs at Google. We automatically examine those legacy violations and make sure developers will gradually clean them up. Now let's see some empirical results about deploying API hardening at Google. First, effectiveness. Since the first quarter of 2018, when we started adopting API hardening, the proportion of DOM access among all externally reported vulnerabilities has been declining, as shown by the blue curve. On the other hand, the ratio of DOM accesses caused by legacy code has been increasing, as shown by the red curve. The two results showing that it is much harder to find DOM access vulnerabilities in new code that uses hardened APIs. As for operational cost, we collect the weekly numbers of Q&A activities and exemption requests related to API hardening. And we can see that the numbers were high in the first few weeks. And then after that, they quickly dropped to a fairly low level, which can be handled by a small number of security experts. These data show that even at Google scale, the cost of API hardening is totally manageable, if not cheap. Then at last, we have the number of legacy violations over time, and we can see that the number has been constantly decreasing, suggesting that Google has been able to steadily reducing its technical debt related to XSS. And combining all the empirical results, we can draw the conclusion that API hardening is an effective and practical solution to preventing XSS in large-scale web development. That's all for today. Thanks for coming, and I'll be happy to take any question afterwards.
Okay, welcome back to this session about security vulnerabilities in different domains. This is the third and last paper in this session presented by Pei Wang and colleagues from Google. If it's not secure, it should not compile, preventing DOM-based cross-site scripting in large-scale development with API hardening. I wonder if there's already some questions from the audience to Pei. Okay, I don't see any, but I have a question, or really a curiosity more about the acceptance of the developers regarding this approach. So you show some number in the paper, but more qualitative feeling for it. Have you been talking to developers, which I guess it's going to be quite many of them, since many of Google products are web-based. So.
Yeah, that's a very interesting question, because part of my job, as we stated in the paper, is to help people deal with all the problems they come across when trying to use those hardened APIs. Basically, each of our teams do a week. It's a rotation. So I feel, in general, if we just not consider Google's culture, in general, I can feel there will be a lot of pushbacks from developers that are, say, if they want to adopt this approach in the beginning. Something similar to using a new programming language like Rust, which can feel a bit clumsy at first, but then after you start enjoying the benefits of this and get used to the patterns, for the hardened APIs, I would say the resistance becomes softer. But you definitely need a lot of training and a lot of help. You need to be responsive to the questions and all the kind of problems people come up with. But we feel this is a good investment, because especially for a business like Google, if you have a problem, even the slightest kind of problem, it can go big. And in general, Google has a culture of valuing security a lot. So people go through training when they joined. They have other security practices to follow in the company. So I would say this works probably a lot better in Google than average. But part of our goal of publishing this paper is trying to convince people that this is something worth considering in your own project, and it's totally doable if you do this thing right. The operational cost would be very modest.
And also, still regarding motivation for developers, how about tooling, for example, to support them in the transition?
Yeah,
you can say something about it.
Yeah, we actually we currently have started a app project to open source all the stuff we use internally in this regard, like the static analysis tool mentioned in the paper that helps you identify all the problematic API uses, and also the alternative secure version of the APIs. They're both on GitHub. They're not 100% mature, but we will, gradually. We made a commitment to make all the available pieces internally also, usable by open source developers. And we actually have initiated an effort to standardize this hardened API idea as a new web security proposal. It's called Trusted Types, and we will keep publishing and blogging about how this idea can be applied to open source community or other companies.
Right. That's interesting. Thanks for the answer. Actually, I think there's a question in the chat from Manara Lafi on this as well. For legacy software transformation to the process of hardening the web applications.
Yeah, that's very good insight. We actually have that internally. There are some general code refactoring tools, both inside and outside Google. I think for this work particularly, it's about writing the right patterns. Because we're dealing with a subset of the problems, we only care about cross-site scripting. So I think instead of relying on a particular tool, it's more about writing the right patterns to help people deal with their legacy violations. Actually, whenever we introduce a new check inside Google, we do a large-scale code change that modifies like thousands of files in a single change to help people migrate off their technical debt. We will open source some of the internal toolings as well in the future. So bear with us, and hopefully this can be useful to other developers as well.
Mm-hmm. Thank you, Ben. Is there more questions? Sorry, is there more questions? I don't see any. But just to touch upon, I mean, the process that developers have to follow. Did you, in the transition, I mean, did you consider this as an item that you track in your backlog? Was it considered like that, or how was the process for rolling out the new API, for example?
Yeah. So basically, so there are several options we have. But first of all, when we try to release a new hardening rule, we do not want to break existing code because they can be supporting critical business. We put them into the you can say the backlog or into a legacy exemption list, and then we will roll out those automated refactoring tools to get rid of most of them. There are several cases where getting rid of the dangerous APIs can be a little bit difficult because it's tied deeply into the design. So some framework want to expose a dangerous API, say set attribute, which can be really hard to get rid of because a lot of downstreaming code will be relying on that API. We have some standardized process inside Google to propose and refactor those APIs, which I think could be good reference for the outside audience. Yeah. But basically, yeah, we don't want to break things. We put them into backlog, and then we clean them up later, either by ourselves or we can invite the team maintaining the code into a say fix-it event. They spend a week or two working with us to remediate their problems.
Right. Okay. Thank you so much, Ray. Left before the end of this Q&A, and then there will be a discussion room to interact with the author. So I wonder if there are any literally last-minute questions from the audience. Otherwise, let me thank you, Pei, for the great work, and thank you everybody who attended this session. I will move now out, and in the last 30 seconds, if there's a question for you, Pei, feel free to answer. Thank you again, everybody. See you.